In this video, we're going to talk about the properties of the definite integral. So let's start with property 1. This property says that if you integrate from b to a of f of x dx, this is equal to, well, notice before we say what it's equal to, that we've written this in a way that's different than we normally would write it. Normally we would write the integral from a to b with the a at the bottom and the b at the top. Here I've written it as the integral from b to a. This is not the same thing. In fact, this is the opposite of the integral from a to b f of x dx. Now, why would this be true? Well, suppose that we're trying to construct this definite integral from b to a. In order to do this, we need to compute delta x. Delta x is the upper limit minus the lower limit divided by n. That's delta x. But notice that this is the opposite of what we normally have, minus b minus a quantity over n. So you can see that delta x is the opposite in this case of what it normally is. And that's where this minus sign comes from. It's actually this minus sign here. So if we write the Riemann sum that is supposed to give us the definite integral on the left, that's going to be the sum of k from 1 to n, f at xk times delta x. But delta x is a minus b over n. And this is equal to the opposite of the sum of k equals 1 to n, f at xk times b minus a over n. It's all because of this a minus b being the opposite of b minus a. That's where this minus sign comes from. So the one on the left, this, as you take the limit as n goes to infinity, this will go to the definite integral from b to a of f of x dx. And the one on the right will go to minus the integral from a to b f of x dx, which is the property we started with. The next property, property 2, is the integral from a to a of f of x dx. This is equal to 0. There are a couple of ways of thinking about this. If you imagine that f is a positive function, for example, and you want to ask what the area is underneath the curve, let's suppose you want to ask the area between a and a. Well, between a and a, that's just a straight line. There's no area there, so the area is equal to 0. Another way of looking at it is again by computing delta x. Delta x in this case is the upper limit minus the lower limit divided by n, but a minus a is 0 over n, which is 0. Just a reminder, when I say the upper limit of integration, I'm talking about the number which is on top of the integral symbol. The lower limit of integration is the one that's on the bottom. Well, this is our second property. What's our third property? Our third property is what we call linearity, or at least one of the linearity properties. The integral from a to b of the sum f of x plus g of x dx is equal to the integral from a to b of f of x plus the integral from a to b of g of x. The way we often say this is we say the integral of the sum is the sum of the integrals. Integral of the sum is the sum of the integrals. This is also true because of the way we construct the definite integral as the limit of Riemann sums. And this property is true for sums. On the left, you're going to have the sum over k from 1 to n of f at xk plus g at xk times delta x. but the sum of a sum is the sum of a sum. Well, that's a funny way to say it. What I mean is this is equal to the sum from k equals 1 to n f of xk delta x plus the sum k equals 1 to n of g of xk delta x rather. Okay. Let me just write this a little bit over to the right there and move the other one a little to the left. Now the one on the left, the sum of f plus g, that goes to the integral from a to b of f plus g. On the right you have a sum. The first Riemann sum goes to the integral of f of x dx, and the second one goes to the integral of g of x dx. Now both of these go from a to b, and that's why this property is true. It's true for integrals because it's true for sums. There's nothing particularly special about a plus sign here. You can replace it with a minus sign. The integral from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. So just like the integral of the sum is the sum of the integrals, the integral of the difference is the difference of the integrals. And that's property 3. Property 4 is the other linearity property. Namely, it says the integral from a to b of k times f of x dx is equal to, and here k is a constant, k times the integral from a to b f of x dx. K is any constant. K is any constant. So if you have a definite integral, you can take a constant out. A constant multiple, that is. If you're multiplying by a constant, you can take it out. Why is this true? This is true for the same reason as the others, because it's true for sums. If we start with the sum of, we better call it j equals 1 to n of k times f at xj delta x, I can take out that k because it's a constant multiple. And that's the sum of j equals 1 to n f of xj delta x. And of course, the one on the left goes to the integral on the left, the integral from a to b k times f of x dx. And the one on the right, of course, goes to k times the integral from a to b f of x dx. 3 and 4 together, 3 and 4 make up what we call the linearity properties. Anything that satisfies these properties, namely that something of the sums is the sum of those things, or if you can take out a constant multiple, these are what we call linear. These linearity properties allow us to compute integrals that maybe otherwise we wouldn't be able to do. Let's look at an example. Evaluate the following integral. The integral is a definite integral from 0 to 5, and the thing we want to integrate is 2 times x plus the square root of 25 minus x squared dx. Now this is something that perhaps at first it doesn't look like we know how to do, because right now we only have 2 methods at our disposal for computing definite integrals. One, using the limit of Riemann sums, which is always difficult to do, even under the best of circumstances. And the second method, is to reinterpret things in terms of area under the curve. Now, finding the area underneath this curve might be a bit challenging. However, using the linearity properties, this is equal to 2 times the integral from 0 to 5 of x dx plus the integral from 0 to 5 times the square root of 25 minus x squared dx. And each of these we know how to do. Let's look at the one on the left first, the integral from 0 to 5 of x dx. Let's just graph that function f of x equals x. It's going to look like this, or like that. This is x, this is y equals x. And we're going from 0 to 5. 1, 2, 3, 4, 5. There it is. This point right here is 5, 5. And what we're looking for now is we're looking for the area underneath the curve. Well, this particular curve is a straight line, and the area underneath it is given as the area of a triangle. So the area is equal to 1/2 times the base, which is 5, times the altitude, which is also 5. So we can just write that as 25 over 2. That's the first curve. So that tells us that the definite integral from 0 to 5 of x dx is 25 over 2. Well, what about the second curve? This we can also graph. Again, we want the xy axes. But what about this curve, y equals the square root of 25 minus x squared? Now this may or may not be obvious, but this is the part of a curve for a circle. If we square both sides, and then add x squared to both sides, we have x squared plus y squared equals 25. So this is a circle with radius 5. So we have, again, 1, 2, 3, 4, 5 right to here. 1, 2, 3, 4, 5. So we're looking at a circle having radius 5, which is something like that. Now we're only looking at a quarter of the circle because we're looking at the region from 0 to 5. That's the interval we're looking at. If you look at our integral, it's the integral from 0 to 5. A is 0, b is 5. So we're looking at the interval from 0 to 5. We're only looking at the top half of the circle because our equation is y equals the square root of 25 minus x squared. The square root symbol indicates the positive square root. This is sometimes called the principal square root, but it's the positive square root. So we're only looking at the positive part. So we're only looking at the top half of the circle. Well, what is the area of this region? Well, we know how to find the area of a circle. We have a formula for that, which tells us that it's pi r squared. So in this case, the area is equal to pi times r, which is 5, squared. But of course, we're only looking at a fourth of the circle, so divide it by 4. So that gives us 25 pi over 4. And that is the second of these two integrals. 25 pi over 4. So in that case, our answer is the sum of these two things. So it's 2 times the definite integral from 0 to 5 of x dx, which is 25 over 2, plus the definite integral from 0 to 5 of the square root of 25 minus x squared dx, which is the area underneath the quarter circle, which is 25 pi over 4. And of course, you can simplify this as 25 plus 25 pi over 4. Our next property is very intuitive from a geometric point of view. And it says that the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. Let's draw a picture of this. So let's suppose, for the sake of argument, so we can talk about things in terms of area, that our function is non-negative. So let's say that it looks something like this. So this is y equals f of x. The basic idea here is that you're going to mark off a spot that's A and mark off a spot that's B. And let's just draw these vertical lines up to the curve, like so. Now the claim is that if you pick a spot C in between these two, and let's draw the vertical line there as well, then the result is not just one region, but now two regions. The first region corresponds to the first integral. So if you look at the first definite integral here, it's the integral from a to c of f of x. So that's the area underneath the curve f of x between a and c. So that's this region right here. The second definite integral is the definite integral from c to b of f of x dx. So that's the area underneath the curve between c and b. Now what about the third definite integral? The third definite integral is the definite integral from a to b of f of x. Now that's the area underneath the curve from all the way to a to all the way to b. So that's the whole thing. So in other words, what this property is telling us is that the whole is equal to the sum of the parts, which, geometrically speaking, is very believable. Now, what's neat about this is that it's also true if C is not between A and B. So when C is between A and B, and the function is non-negative, we can view it geometrically, and then it makes sense. But in fact, f doesn't have to be non-negative all the time, and C can be before A or after B, and it's still true. Let's look at an example. So for our example, let's evaluate the definite integral, let's say from 2 to 6 of x over 2 dx. So in this case, our function f of x is equal to x over 2. And we're interested in the definite integral from 2 to 6. This function, x over 2, is positive over that interval. Let's graph it just so we can have a look. So this is the x-axis, this is the y-axis. 1, 2, 3, 4, 5, 6. So this is 6. We're interested in the interval from 2 to 6. Our function is x over 2, so that means it passes through the point where x is equal to 2 and y is equal to 1, and when x is equal to 6, it passes through y equals 3, which is here. It does pass through 0, 0, so we now have 3 points on this line. So it looks like this. This is y equals x over 2. Now the thing that we're interested in is the area underneath this positive curve between 2 and 6. So this is the function that we're the interval that we're interested in. We want to compute this area. This, of course, is the area of a trapezoid. Now, how would we compute this? Well, the easiest way, if you don't happen to remember the formula, is to view it in terms of the triangles that make it up. So notice that we have a large triangle and a small triangle. The large triangle is this triangle from 0 to 6. There's a big triangle there, and we can compute the area of that big triangle. And then there's a small little triangle right here. Let me just make that small little triangle blue so that way I can call it the blue triangle. So geometrically, the area of our trapezoid is equal to the area of our big triangle minus the area of our smaller blue triangle. And we can actually compute all of these very easily, because for the big triangle, the base is 6 and the height is 3, and for the small triangle, the base is 2 and the height is 1. So we can compute these. 1/2 6 times 3 minus 1/2 2 times 1. All right, well that's fine, and we can actually compute these. So this one, 6 divided by 2 is 3, so this is 9, and 1/2 times 2 is 1, so this is 1. So 9 minus 1 is 8. All right, we can do it geometrically, but we can also do it using the properties of the definite integral. So this was the geometric approach, the geometric method. But let's do it using the properties of the definite integral. So what I'm looking at in this case is I'm imagining that a is equal to 0, b is equal to 6, and c is equal to 2. So I can integrate from 0 to 2 of x over 2 dx plus the integral from 2 to 6 x over 2 dx equals the integral from 0 to 6 x over 2 dx. Now the thing that I want to find out is this middle integral, the integral from 2 to 6 of x over 2 dx. What about this first one here? Well, the first one is 1/2 times the integral from 0 to 2 of x dx. And the last one is 1/2 the integral from 0 to 6 of x dx. So let's look at our first integral from 0 to 2. So now we're looking at the definite integral of the function y equals x, or f of x equals x, and we're going from 0 to 2, like so. Now the area here, of course, is the area of a triangle. It's 1/2 2 times 2, which of course is 2. Now over here we have the same sort of thing, but now we're looking at the interval from 0 to 6. 0, let's do 1, 2, 3, 4, 5, 6, like so. But it's still the same line, this line, y equals x. And of course, once again, we can compute the area. So the area here is 1/2 6 by 6, which is, of course, 6 times 3 is 18. Okay, well now we can put all of this stuff together. So on the left we have 1/2 times 2 plus the integral from 2 to 6 x over 2 dx is equal to 1/2 times 18. On the left we have a 1, on the right we have a 9, so now you just solve for the unknown quantity, and in that case you end up with the integral from 2 to 6 x over 2 dx is equal to 9 minus 1, which is 8, which is what we had before. The last properties that we want to talk about are what are usually called the comparison properties. So the first of these says that if you have a function, f of x, which is greater than or equal to 0 for all x in some interval, say a less than x less than b, then the integral from a to b f of x dx is greater than or equal to 0. Basically what this is saying is that if your function is not negative, then there's some area underneath it which is going to give you a positive number. That's basically the idea. Property B, if f of x is greater than g of x for a less than or equal to x less than or equal to b, then the integral from a to b of f of x dx is greater than or equal to the integral from a to b g of x dx. And here, again, the idea is geometrically simple, at least if you imagine that the functions are positive. So if you imagine that the functions are positive, then this first integral, the integral of f, is the area underneath f. And the integral of g is the area underneath g. If f is bigger than g, then that means the graph of f is above the graph of g. So if we try to graph it, it's going to look something like this. Again, I'm assuming that these functions are non-negative so that I can have some geometric intuition. So let's say y equals f of x is up here, and then we have some y equals g of x below that. The g integral is the area, well, I should probably mark out an a and a b. Then the integral of g from a to b is going to be the area underneath g. And the f integral, the integral from a to b of f, that's the area underneath f. And what you can see is that there's more area underneath f than there is g, because in fact, the area underneath g is included in the area underneath f. So that's why the definite integral is going to be bigger. That's the second one. The third one says if little m is less than or equal to f of x is less than or equal to capital M on the same interval, so let's say for a less than or equal to x less than or equal to b, then we can say something about the definite integral. The definite integral from a to b of f of x dx is going to always be bigger than little m times b minus a and smaller than capital M times b minus a. Now what's the basic idea here? Well, here we're imagining that capital M is an upper bound and little m is a lower bound, so the maximum and minimum. So imagine that we have a graph like so, and imagine that you have some function that looks something like this. Let's say that this is y equals f of x. And let's say that over here is a, and over here is b. Well, on this interval, the minimum value that f can take on is right here. Let's call that little m. That's at this point right there. The maximum value appears to be right about here, and let's call that capital M. So you can see that little f, the function f is always between little m and capital M. So the integral in between, the definite integral of f, is the area underneath the curve. That's fine. Well, what is little m times b minus a? Little m times b minus a is the area of a rectangle. Namely, it's the area of the rectangle that has base a minus b and height little m. So if I shade it in, it's this region right here. The area of this rectangle is little m times b minus a. And you can see that that's less than the area underneath the curve. Well, what about capital M times b minus a? Well, that instead is the area of a much larger rectangle. It's this rectangle right here. The height of this rectangle, as you can see, is capital M. The width is still the same, so the area here is capital M times b minus a, and that gives us this quantity. And you can see that that area contains all of the curve from a to b, all of the curve in the area underneath it, and that's where this property comes from.